Okay, well, I'm extremely happy to have Alberto Nicolis from Colombia. We've been colleagues for a long time, and once upon a time we even wrote a paper together. And I always enjoy his seminars. He works on a very, very wide variety of stuff, and I always learn something from him. So let's go ahead, Alberto.
So thank you very much for the invitation, and maybe next time I'll be able to come in person.
Yeah.
So it's been a while. It's been a while. So now there's also Nemanja. Good. I was wondering what happened to him. So I want to tell you about a paper I published a year ago, more or less, with my students, Joanna and Guanghao. Guanghao is in the audience today. And it's a technical paper about technical computation, but somehow we find it interesting because there's something happening there, and we wonder whether it could have anything to do with a possible approach to the cosmological constant problem, okay? So I don't want to review the cosmological constant problem because that's, in my experience, a recipe for disaster, in the sense that everybody has their own opinion about it, and it's always slightly different, and so it derails completely the conversation. So I'm sure you guys know what the cosmological constant problem is. You have your own opinion about it, and maybe you don't care, or maybe you do care. I just want to somehow present to you an analogous problem or phenomenon, let's say, in a completely different system, and how things work out. I want to show you how things work out there, okay? So in particular, this system I want to talk about is a framid, which is a hypothetical state of matter that I will review in a second. So let's take a quantum field theory, relativistic quantum field theory viewpoint. So from that viewpoint, we can think of states of finite density states of matter, or let's call it in quotes condensed matter, as states in relativistic quantum field theories that break boosts spontaneously. And maybe they also break other symmetries, but at least they break boosts. That's the definition, but that's perhaps what we mean by finite density of matter, that there is a preferred reference frame, which is the rest frame of the matter we are talking about. That breaking is spontaneous, of course, so boosts are a fundamental symmetry of nature, but we are used to the fact that there can be states. In fact, most of the states that we consider, that we experience in daily life, break boosts spontaneously. So according to this viewpoint and characterization, then ordinary media like fluids, superfluids, solids, and supersolids are described by now by well understood effective field theories that include a lot of technology having to do with spontaneous symmetry breaking and the Goldstone phenomenon, if you want. And of all these systems that are on this line here, solids, superfluids, and supersolids can also exist at finite temperature. Ordinary fluids, as far as we know, only exist at finite temperature. And in particular, there's always some associated dissipative phenomena, and it's tricky to take that into account in an effective field theory language. But there's been a lot of progress recently in that as well. It so happens that Fermi liquids are also well understood from an effective field theory viewpoint, but their relationship to the spontaneous breaking of boosts is quite peculiar. And if I have time, in a few minutes, I will quickly mention what's peculiar about it, okay? So these framids that I want to talk about have not been observed in nature. However, they correspond to the simplest possible symmetry breaking pattern, in the sense that, for instance, for the states that can exist at zero temperature, the solids, the superfluids, and the supersolids, on top of breaking boosts, they also break other symmetries. The superfluids break an internal U1 symmetry, and solids and supersolids also break translational symmetries. Okay, they don't just break boosts. Fluids are more complicated, again, because they happen at finite temperature, so I don't want to go in that direction. Fermi liquids only break boosts, but there's no associated Goldstone boson for them. It turns out that what saturates a Goldstone-like theorem, in the case of a Fermi liquid, is a particle-hole continuum. So there's no single particle Goldstone bosons associated with the spontaneous breaking of boosts. It's a particle-hole continuum. So to this characterization, the Framids would correspond to the simplest possibility in which you break boosts and you have Goldstone bosons for that breaking, and that's it. And they're not realized in nature, as far as we know. And so let's see why it's tricky to find a system that only breaks boosts and has Goldstone bosons for them, and everything works out as usual. Let's see why that's not obviously easy to realize. So suppose you break boosts, I denote the generators by K, but you don't break translations or rotations, okay? So the stress energy tensor operator by symmetry can take a 0,0 expectation value and an ij expectation value proportional to delta ij. So I call those entries rho, the energy density, and p, the pressure, okay? This is the most general expectation value the stress tensor can have in this situation. And suppose now I implement the usual Goldstone boson ideology. That is to say, whenever I have a spontaneous symmetry, I can think of the Goldstone boson as whenever I have a spontaneous breaking for a symmetry, I can think of the Goldstone field as being a transformation parameter for that broken generator, weakly modulated in space and time. Okay, and that's why, for instance, usually it's only derivatively coupled, because I know that in the limit of 0 derivatives, I'm just applying a symmetry transformation to the vacuum, so I'm doing nothing. Okay, so let me introduce such a Goldstone field, eta. It's a triplet, because I'm breaking a triplet of generators. It's a triplet under rotations. Let me introduce the Goldstone field, and let me boost the stress energy tensor with a weakly modulated eta parameter. And now let me look at what happens to lowest order in eta, so first order in eta, but 0th order in derivatives. Okay? So the total energy, P0, changes by the transformation of T00, which is now the transformation of T00 is T0i eta I, integrated in D3x. T0i had a vanishing expectation value on the ground state because it would break rotations, that expectation value. So I get 0. So there's nothing peculiar about the energy. However, the momentum, if I look at how the total momentum transforms, I get that it transforms by the volume integral of the transformation of T0i, which now gets contribution from T00 and from Tij. Okay, I'm applying a Lorentz transformation. The transformed T0i gets contribution from T00 and Tij. And if you look at numbers and signs, you discover that this is precisely rho plus p times eta. So this is the variation of the total momentum of the system if I apply a symmetry transformation modulated in space-time. Now, why it's peculiar? Because, you see, it starts linear in the Goldstone field. The Goldstone field has an expansion which is A plus A dagger in terms of single particle states. In particular, it's not A dagger A. However, I assumed that the translations are unbroken. If translations are unbroken, the excitations should be eigenstates of translations, meaning should be eigenstates of momentum. So the momentum should start at quadratic order in the Goldstone field and have a structure that has some A dagger A, so you just count the number of Goldstone particles, okay? So Goldstone particles are not eigenstates of the total momentum in this system. So if you break boosts, apparently there is this paradox. So how does ordinary states of matter get around this? Yes, Marcus?
Stupid question. So that expression also looks like, even forgetting about the fact that it's linear, that it's not 0 if eta is a constant.
Correct. Yeah, that's a good point. Yeah, that's a good point. But however, you see, there's no real the fact that it's non-zero when eta is a constant just tells you that this expectation values are not invariant under boosts, which is consistent perhaps with the pattern of symmetry breaking. No? Let me tell you how ordinary matter gets around this. Maybe it's related to it. Okay. So how do things work out in general? So in the case of a Fermi liquid, as I told you, there's simply no local Goldstone field. There is a Goldstone theorem. You can go through the Goldstone theorem for spontaneously broken boosts. So the Goldstone theorem tells you there's going to be gapless states. However, you can check that the spectrum of a Fermi liquid is such that near the Fermi surface, you have gapless bosonic states that are simply particle-hole pairs. But these do not have the, let's say, normalization or even the locality properties of single particle states. They're really two particle states, meaning there's a particle and there's a hole, and they form a continuum. So this ideology about local Goldstone fields does not apply to a continuum made up of particle-hole states. For solids, translations are also broken. So there's no need for the Goldstones of anything to diagonalize translations. They're spontaneously broken. Okay. For superfluids, there is this phenomenon that is called the inversion constraints. So whenever you break spontaneously space-time symmetries, the counting of Goldstone's bosons is slightly different, meaning that in general, depending on the algebra, you have fewer Goldstone fields than broken symmetries. And in particular, for superfluids, you can check that the pattern is such that the boost Goldstones can be expressed at linear order as gradients of the U1 Goldstone. Okay, this is the statement that the superfluid velocity, for instance, is the gradient of the superfluid phase. Okay, we are used to it in non-relativistic superfluids. And so when I integrate now this expression that I had here, rho plus p eta I, well, that eta I is a gradient that integrates to 0. Okay, so the linear term for superfluids is just not there. These famous Framids I want to talk about, okay, have the peculiar property that this argument is irrelevant for them, because for them, even though boosts are broken, rho plus p, which would be a sign, it's being 0 would be a sign of unbroken Lorentz invariance. For them, rho plus p is 0, even though Lorentz invariance is spontaneously broken. So I'm gonna tell you how that comes about. Okay, but for the Framids, the solution, as we will see, is that rho plus p is just 0, which is the same as saying the expectation value of the stress energy tensor is proportional to eta mu nu, even though boosts are broken. So if this is true, there's some sort of naturalness problem or a hierarchy problem here. There are some entries in some expectation value that are 0, even though there's no obvious selection rule that forces them to be 0. So this will be my analog of the CC problem. But let me elaborate a little bit on it.
Sorry, your rho and p are function of x or is constant?
Say again, sorry?
Your density rho and momentum density p is constant or function of x?
Now, in this case, I'm considering unbroken translations, you see? So if I have unbroken translations, rho and p are constant in x.
Okay.
I mean, he's talking about the ground state. You're talking, another way to say it, I think, is you're talking about the ground state.
Yeah, that's a good, I don't know, because I cannot explore whether this is the true vacuum, or maybe some vacuum at finite density for something. No, like I have no access to the full non-perturbative Hilbert space. I'm just gonna do effective field theory close to this state. So I'm considering a state with unbroken translations and unbroken rotations, but broken boosts. I don't know if it's the true ground state. In the same sense that if I give you a piece of solid, well, maybe it's a ground state for that value of the baryon number, but it's not the absolute ground state. No, the absolute ground state of all the quantum field theories that we know and love is the Poincaré invariant vacuum. Is that okay, Marcus?
Yeah. No, I was just
okay. Let's say it's the ground state of this effective theory. Then I don't know what happens outside the effective theory. Okay, so let's talk about this effective theory. So there's different ways we can construct it. It turns out that they turn out to be equivalent. Okay, so the simplest way is to just pick some order parameter for the breaking of boost. Say something that transforms under boost. The simplest thing is a vector operator, but one could do the same analysis with some tensor representation, for instance. So I take a vector operator and I assume that it breaks boosts, but it doesn't break translations and rotation. So it must have an expectation value that is aligned with time. Okay, in that case, I'm breaking boosts without breaking spatial symmetries. And then I introduce the Goldstone fields exactly like I was saying earlier, meaning I now perform the broken boost transformation modulated in space and time with this parameter eta of x. And I make it act on the expectation value. So it's in the U1 case, for instance, if I were to do the U1 Goldstone effective theory like this, I would take the expectation value for some complex field, and I would now modulate it with some phase e to the I pi x. And so I would write down an invariant action for phi, expand in pi, and that would be my effective theory for pi. Here I can do the same for eta. There is a more general construction, which is the Cosette construction, which does not rely on choosing a particular representation for the order parameter, but it turns out to give exactly the same result. So this is perhaps more intuitive what we are doing. Okay. So now, so this V mu is not a fundamental field in any sense. It's just a placeholder for this combination of Goldstone fields, in the sense that if I contract now the mu indices in the usual ways, I know that I end up with an effective theory that is invariant under boosts, non-linearly realized on the Goldstone fields. Okay, so this is just a technical trick to implement non-linearly boosts on the Goldstones. So I write down my effective theory as a bunch of covariant terms for V mu's and derivatives. Okay, so to lowest order in derivatives up to integration by parts, there's only three terms. To all orders in V mu, because remember, the norm of V mu is fixed because the VEV of V mu has a certain norm, and that norm does not change under boosts. So the Goldstones do not affect the norm of V mu. So it's like, it's as if the radial mode has been integrated out, if you want. Okay, so there is this constraint. And to lowest order in derivatives, but to all orders in V, I only have the first line in the effective theory here. Then I can add higher derivatives, and crucially, I probably have a cosmological constant, because I know that the cosmological constant problem is always there. So even if I don't put the cosmological constant at tree level, I'm going to need it as a counter term, so I might as well put it from the get-go. Okay. So when I derive the stress energy tensor, you can derive the Noether tensor, or you can derive the Einstein-Hilbert tensor. You have to be a little careful because of this constraint. To derive the gravitational stress tensor, you have to use the tetrad rather than the metric, okay, because that behaves better under Lorentz. Anyway, regardless, you get the same result up to the usual improvement terms. But the fundamental property of the stress tensor that you're going to get is that it involves derivatives of this order parameter V plus cosmological constant times eta mu nu. Now, all these derivatives of V, when I check what the value of the stress energy tensor is on the ground state, all these derivatives of V give me 0, because the ground state has this. I'm doing a tree-level statement now. I'm making a tree-level statement now. No, at tree level on this background configuration, all those derivatives are 0. So I see that this effective theory, at least at tree level, gives me a stress tensor whose value on the background configuration is proportional to eta mu nu, even though Lorentz is broken. Now, Marcus, this reminds me of what happened for the ghost condensate. But in that case, if I remember correctly, this property, so the fact that T mu nu was proportional to mu nu, was only true at the very specific point where P prime is 0, at the minimum of the kinetic function somehow. Okay, but it turns out to be, I think it's related, but I haven't found the.
Right, the only place where away from that, you did have these linear excitations. It's really the same statement, but you know, like you showed before, we have a linear excitation in eta. The points where rho plus p was not zero are also, if you think about it, it's the same statement, right? It's the terms where those are absent. So somehow for yours, right, because that's just saying that the potential is minimized with respect to the Goldstones. And so, yeah, but yours somehow is a flat, it's like ours was true at the minimum of the potential, and your potential is flat. It's like that.
Well, but notice that I have a constraint, okay? Because my Goldstones cannot change the absolute value of V. So
right.
I don't have a flat direction really. I only have this stationary state, whereas you guide at a continuum of stationary states, and for the one that is somehow selected when you expand the universe, let's say, by an infinite amount of e-folds, you end up with an expectation value like this. Yeah, I don't know what if there is a real correct, but anyway, it looks similar. I don't know if there is an interesting connection. But okay, let me just make this the comment that for now, at tree level, it appears that the stress tensor is proportional to eta mu nu, so it doesn't break Lorentz, even though by definition the system does break Lorentz spontaneously.
But I think you have some correction from loop level, right?
Excuse me?
You have some correction from loop level. That no symmetry, you should have that somewhere.
So now I'm going to talk about what happens at loop level.
Okay.
Very good.
Yeah, that's exactly the question we want to address, and we don't want to have any preconception. Meaning, this is already mysterious at tree level. Now the question is, okay, if at loop level it survives, we have some sort of cosmological constant-like situation, maybe in which some things that should not be zero are mysteriously zero. If it doesn't survive at the loop level, we still have a mystery, because I mean, this was the most general effective theory consistent with the symmetries, and we know that it should include all possible local counter terms. So it's not obvious how loop corrections could screw up this without changing the usual rules of renormalization theory. But let's say without any preconception, we are going to check what happens at one loop. Okay, so
can I ask a question before you go to that?
Yeah.
There's you know, for ordinary field theories, there's this Weinberg argument, right? That just says why is the cause making the, I guess that's for the zero of the cosmological constant. So maybe that's different. I was going to ask, what about the Weinberg argument that tuning the cosmological constant is requiring the vacuum energy and its derivative to be zero at the same place? But I guess this is not that, right? This is
I'm not addressing the cosmological constant problem at all. This is just an analog.
I guess I'm asking, is there a Weinberg-like argument or something?
Well, that's a good question. That's a good question. But you see here, I mean, I think Weinberg would be happy in the sense that the effective theory, the most general effective theory that you can write down, consistent with the symmetries, has these properties. So there's not even a need to relax to this state.
No, I know, but in a generic theory, if you said, I don't want relativistic invariance and I want rho plus p to be zero, I would guess that there's a Weinberg-like theorem that says, oh no, look, these are independent conditions, but somehow this evades that. So I'm just wondering.
Yeah, that's a good question. I don't know. That's a good question.
Okay.
Yeah, that's a very interesting question. You're referring to the argument about relaxing the CC, no?
Yeah, that's the argument for relaxing the CC, but I think because you're using rho plus p equals zero as sort of a proxy or analog of that.
Yeah.
You have the same question.
Yeah, good question. I don't know. That's a very good point. I don't know. Okay. But anyway, so I think we understand what the mystery is. Now, the mystery is we have a ground state that breaks Lorentz. The stress energy tensor doesn't. On the other hand, there shouldn't be any selection rule enforcing that the stress energy tensor be Lorentz-invariant. And again, this is reminiscent, although it's not the same, of course, as the CC problem, in which we have something the expectation value of the stress tensor is 0 or approximately 0 compared to whatever natural value you should have, natural in quotes, again, because everybody has a different definition of natural. And there's no selection rule, apparently, enforcing the vanishing of the expectation value of the stress tensor. So if you want, here we have a situation in which, if this survives loop corrections, we have the vanishing of the Lorentz violating entries in the stress tensor is not enforced by any selection rule, but still it happens. So we'll see whether it happens or not. Okay, so let's check whether this survives quantum correction. So I take now that effective theory, I expand in Goldstone fields around that background configuration. And I have a kinetic energy, I have gradient energies with different propagation speeds for the longitudinal and the transverse excitations, so pretty much like phonons in a solid. Plus I have interactions, okay, with a bunch of derivatives. And now, it's clear in this effective theory that Lorentz invariance is not manifest at all. We know it's not linearly realized, but at every finite order in eta, there's no Lorentz invariance. By definition, a nonlinear realization couples different orders in eta. So it's not obvious now how doing loop computations in this theory about this state is going to preserve the Lorentz invariance of the expectation value of the stress tensor. Okay, so what we did was we computed the expectation value of the stress energy tensor at one loop. So at one loop, remember, the stress energy tensor expectation value at one loop is essentially a vacuum bubble that only has to do with the quadratic part of the action. If you were to consider interactions, you would have vertices that would be a two-loop diagram, three-loop diagrams, and so on. Okay. So we're going to take the quadratic part of the action. And for now, only this. And later, for a number of technical reasons, I'm going to couple it to some other fields, better fields, and see what happens in their presence as well. Okay. So there's two technical complications. The first has to do with the measure, the path integral measure. So, I mean, I phrase it in terms of the path integral, but the same subtlety arises in the canonical formalism. Okay. At the level of the path integral, if I were to use the measure d eta, that's not Lorentz invariant, okay? Now, so one has to be careful about that, and one can check that using a Lorentz invariant version of that measure, it would be like for pions using the measure d pi instead of a more Lorentz chiral invariant measure, okay? So in the case of the pions, we know that if we use dimensional regularization as a regulator, the measure does not really matter. The determinant that we get from the measure, it vanishes in dimensional regularization. So here is the same. If we use dimensional regularization, the measure does not matter. Okay. And we can also prove, and we did prove, that if we use any other regulator, because later we are also going to use some Pauli-Villar-like regulator, if we use any other regulator, the determinant that makes the measure Lorentz invariant does not matter at one loop. It can matter at higher loops, but not in one loop. So I'm going to ignore subtleties having to do with the fact that the measure is not the trivial measure d eta, which corresponds to doing canonical quantization for the eta field, is not Lorentz invariant. And the second complication has to do with UV divergences. Of course, we are computing a vacuum energy here, and it's going to be UV divergent. Okay. Now, since our question has to do with the Lorentz invariance of that expectation value, we'd better use a regulator for those UV divergences that preserves Lorentz invariance. However, Lorentz invariance is non-linearly realized on the etas, so it's not immediately obvious what a Lorentz invariant regulator is in this theory. So in particular, if I give you a one-loop integral involving the etas, and I tell you, okay, now go to Euclidean space and put a hard cutoff in momentum space in a spherical fashion so that it's Lorentz invariant. It doesn't make any sense because the dispersion relations for the eta fields already have speeds different from one. So the propagators do not look Lorentz invariance in the first place. So why should I put a Lorentz invariant cutoff in the first place? Okay. So it turns out that dimensional regularization is Lorentz-invariant, and I will explain why. And a suitable generalization of Pauli-Villard is also Lorentz-invariant. Okay, Lorentz-invariant. And so we're going to use those, and I will explain in what sense they are Lorentz-invariant. Okay, so since we are going to do computations in a theory that is not manifestly Lorentz-invariant, let me first check how to recover this result, that the stress tensor is proportional to eta mu nu on the vacuum, for a Lorentz-invariant relativistic scalar field theory without any breaking of boosts, but without using Lorentz invariance at all. I'm not going to use manifest Lorentz invariance. Okay, so how do I check this without using manifest Lorentz invariance? So for a relativistic scalar, so I take this Lagrangian and I derive the stress tensor as usual. And now you know that you can regulate, if you want, the expectation value of the stress energy tensor by point splitting. And so in that case, the expectation value of the stress tensor reduces to the limit in which 2 points come together of certain derivatives acting on the 2-point function of the scalar, right? It's like d mu phi, you rewrite it as d mu of the 2-point function evaluated at coincident points. Crucially, in that computation, you use the Whiteman 2-point function without any T ordering, because you are computing an expectation value and there's no T ordering unless you, introduce it by hand. There's no T ordering in the computation. So when you go to momentum space, this is the Whiteman 2-point function for a free scalar field in momentum space, Lorentz-invariant. And those derivatives that I was talking about, d nu, happen to be k mu, okay? So at this level, of course, everything is still manifestly Lorentz covariant. So I could be tempted and use Lorentz invariance now, but let me not do that. Let me use the delta function to integrate in dk0. Okay, so I end up now with this integral here. And now rho takes this form and p takes this form. Okay, these are two different integrals. Apparently, they have nothing to do with each other. In fact, apparently, they are both positive definite. So at this level, it appears hopeless that rho plus p be 0, because these integrals look both positive definite. But of course, this is premature, because both of these integrals are UV divergent. So unless you are careful about the regulator, you cannot conclude anything by looking at them at face value. Okay. In particular, any way of regulating them will not make them both positive definite. So in dimensional regularization, you just compute those integrals, and they happen to be exactly, even though they look very different, one is omega k and the other is k squared over omega k, they give exactly the same result up to the sign. And so rho plus p is 0. So you can just, even without using manifest Lorentz invariance, in the case of the relativistic, you can just check. You can just check that rho plus p is 0. And let me also use Pauli-Villard. So Pauli-Villard, the simplest implementation is this. Now I replace a Feynman propagator with itself minus the Feynman propagator or a much heavier state. Okay, so that the high k limit, the low energy limit, is exactly the same as the original Feynman propagator, and the high k limit is much softer. Now that's enough to regulate log divergences. Here, since we are talking about vacuum energies, we want to regulate a quartic divergence. So we have to do a threefold Pauli-Villard regularization, meaning we have to replace the Feynman propagator with the, sorry, this should be G Feynman. With we should replace the Feynman propagator with the Feynman propagator plus the Feynman propagators of 3 other poles parameterized by these dimensionless alphas and the common large mass scale M, with the residues tuned in such a way that at very high energies, the Feynman propagator goes like 1 over k to the 8th. This regulates quartic divergences, it so happens. Okay, so bottom line is that there's a suitable generalization of Pauli-Villard parameterized by a bunch of order 1 coefficients and a common very large mass scale, so that at low energies you have the same Feynman propagator, but at very high energies you go like k to the 8th. Okay.
Why doing the threefold Pauli-Villard? Can you explain this, please?
Excuse me?
Why do you need a threefold Pauli-Villard?
Because the single Pauli-Villard makes the high energy behavior go from 1 over k squared to 1 over k to the 4th. And since you are integrating in D4k, this is enough to regulate log divergences. Okay? Now, if you want to regulate a quartic divergence, you need the UV behavior of the propagator to be much more suppressed. In particular, you need 1 over k to the 8th. It so happens. Okay. And so, in order to have a bunch of propagators sum in such a way that they go like 1 over k to the 8th, you need 3 of them. You need the original one plus 3 more with different residues and different poles. Okay. This is, I mean, I didn't know about this, but I found out that this is pretty standard in the literature, so it's nothing particularly new. Okay. So again, now these integrals look very different. However, it so happens that this thing, if you choose alpha and c in such a way that the UV behavior is 1 over k to the 8th, regulates both of them, makes both of them finite. The rho that you were getting, so the energy density, now becomes the energy density for the field of mass m plus this particular linear combination of energy densities of fields of mass alpha m. And overall, they sum up to give you something finite. Of course, I mean, there are quartic divergence, but now in the physical mass scale m, sorry, physically, in the Pauli-Villard mass scale m. Okay, so this is your regulator. Notice that very nicely the coefficient of the log divergence is completely UV independent. It does not depend on the alpha parameters that are regulator dependent. It only depends on IR physics, in particular the physical mass of your scalar. Okay, and it matches exactly the log divergence of the dimensional regularization case. So this is a non-trivial cross-check. Okay. And for the pressure, again, you get a similar structure, which is exactly minus rho. So also in this case, rho plus p is 0. Okay. Just to say that even if you give up manifest Lorentz invariance, there is, if you are careful about the regulators and using UV divergent, Lorentz invariant regulators, there is a way to keep track of Lorentz invariance in the final result. Notice crucially that Pauli-Villard, even though it corresponds to new poles with negative residues, so it corresponds to unphysical states, if you want. However, it has the nice feature that it can also be rewritten as certain higher derivative corrections to the Lagrangian. So in a sense, in the language of effective field theory, it's a particularly nice regulator because it corresponds to higher orders in the derivative expansion. So in particular, the standard Pauli-Villard regulator, which would be something like this, I can combine the two denominators like this. And this corresponds, so the denominator corresponds to adding to the Lagrangian something like this, okay? So I guess what I want to emphasize that Pauli-Villard corresponds to a local Lorentz invariant correction to the Lagrangian. So we are going to exploit this. Okay, so let's do the same for our Framid now. So in our Framid case, if I compute the stress energy tensor at quadratic order in the Goldstones, I get these structures. Okay, in particular, I get an integral in d3k of the vacuum energy, if you want, the 0-point energy of the longitudinal Goldstones plus twice, because I have two transverse polarizations, the 0-point energy of the transverse Goldstones. And for the pressure, I get something very similar to what I was getting before, but with different propagation speeds here, okay? So this is very similar to the structure that we had in the relativistic case, but of course there are some non-trivial propagation speeds here. They're not one, they're something slightly different. And also we have to be careful about regularization, because as I said, it's not obvious what it means now to impose certain, that the regulator be Lorentz-invariant. So let's start with Pauli-Villard, okay? So given the similarity, yes?
CT and CL, their ratio is just a pure number, or does it depend on a parameter? What is it?
These are parameters in the EFT, okay? These are the propagation speeds for longitudinal and transverse.
Okay, and it's a parameter.
These are, yeah, these are free parameters in the EFT.
Okay, thanks.
Okay. Okay, so now let's start with trying to adapt the Pauli-Villard ideology. So given the similarity with the relativistic case, the only difference with the relativistic case is in these propagation speeds, okay? And look at this order, of course, longitudinal and transverse are decoupled, because a quadratic order I cannot miss longitudinal and transverse because rotations are unbroken. So if I can do Pauli-Villard separately for the longitudinal and the transverse modes, everything works out. Why? Because the longitudinal Feynman propagator is related to the relativistic Feynman propagator if instead of the speed of light, I use the speed of propagation for longitudinal Gaussians. Same for the transverse one, okay? And so if I can do separately Pauli-Villard for longitudinal and transverse with two independent propagation speeds, I find that the total rho of my framid is this particular combination of the relativistic result times propagation speeds, and P is exactly the same factor that depends on the propagation speeds times the relativistic result. So since in the relativistic case rho plus P was 0, and since here I have a common factor in front, I still find rho plus P is 0. So the only question is, what does it mean for this system to do separately Pauli-Villard for eta L and eta T? Meaning, can I just pretend that I have two decoupled sectors, and I'm going to interpret the first sector as some relativistic sector with a propagation, with a speed of light that is CL, and the second sector with a propagation speed that is CT. So,
sorry, can I ask a completely trivial question?
Yes.
Could you go back to the previous slide? So here it looks like for the density you have omega L plus 2 omega T, but you don't have the factor of 2 in the pressure. Is that just a misprint? Or
Yes.
because it looks like they don't cancel.
Yes, thank you. It's just a misprint. Just a misprint.
Okay.
Thank you very much. Yeah. These are the two polarizations for the transverse modes. So each at quadratic order, everything is simple. Each mode counts factor 1. Thank you. Thank you.
Okay, good. So it's the same with
In
the
fact,
pressure.
I should write it down so I will correct it. Thank you. Okay.
Can I ask a question?
Yeah.
There's something I didn't understand about the last slide where you're saying you're doing Pauli-Villards for the different independently for the different modes. Because somehow I had the impression that the Lagrangian at this order, the free order, was just a sum of the Lagrangian for the longitudinal and transverse. And
yes,
one of them has a CT and the other one has a CL.
Yes.
And now you're just regulating them independently. How can you get a cancellation between those two modes? Is this something I'm not understanding?
No. Sorry. Within each sector, I have the same cancellation that I would have for a relativistic guy.
Okay. All right. So okay. All right. So
because it's because you see it's there is this prefactor that depends on, there is a 1 coming from times this factor that comes from the longitudinal sector, and there's a 2 times this factor that comes from the.
Okay, I got it.
But the cancellation is really between the rho of the relativistic guy and the P of the relativistic guy. So now the question is, what does it mean to regulate the two sectors separately with two independent propagation speeds? So I don't know the rules of the game in general. However, if we insist that Pauli-Villard still corresponds to a local Lorentz-invariant addition to the Lagrangian, higher derivative addition to the Lagrangian, then we are sure that we are not screwing up locality or Lorentz invariance. Okay, so this is a conservative approach. I don't know if there is a more relaxed approach, but if I can find a way to implement the Pauli-Villard independent regulators that I need simply by adding local Lorentz invariant terms in the Lagrangian, then certainly at least this is a regulator that does not screw up locality or Lorentz invariant. So let me try and do that. It's not trivial, it's not easy to do that in principle, because the splitting of eta into the longitudinal and transverse parts is not local. I need to, it's local in momentum space, of course, but not in position space. I need to apply some non-local projectors that extract the gradient part and the curl part. Okay, so it's not obvious that I can do that, that I can split eta into longitudinal and transverse in a local fashion. Also, eta transforms non-linearly under Lorentz, so it's not obvious that now at quadratic order in eta, I can add things to the Lagrangian that are Lorentz invariant, okay? Or that at least don't mess up Lorentz invariance. So it turns out that we can. So let's see what we get. For instance, for the longitudinal guy, if I define the longitudinal Lorentz invariant, it's not really Lorentz invariant, but the modified Lorentz invariant combination, omega square minus CL square K square, I need to replace the longitudinal Feynman propagator with this Pauli-Villard-like propagator that has a K to the 8th high energy behavior, okay? And the CL here is implicitly inside all these KLs, okay? So from the viewpoint of the Lagrangian that I need, the Lagrangian correction that I need to implement that, I just replace all the K square L with box L, where box L is again the same combination of derivatives that I do have for the relativistic box, but with a CL here, okay? So I need this correction to the Lagrangian for the longitudinal eta, plus the similar structure for the transverse eta. So if I'm able to impose that, to add to the Lagrangian these terms in a way that is local and Lorentz invariant, I accomplish what I needed to accomplish. So for locality, one can prove that even though extracting eta L is not a local procedure, extracting eta L from eta is not a local procedure, extracting at least these particular combinations of derivatives that appear in box L is a local procedure. In particular, one can show that this particular delta L is a linear combination of terms like this, in which I have certain local combinations of derivatives, this D is the IDJ, is the matrix the IDJ, acting on the full eta field. So in this way, I can extract this combination of derivatives acting on the eta L and the same for eta T. Okay, so locality, since I don't have to extract eta L by itself, I have to extract certain derivative structures acting on eta, locality is safe. Okay, so I can certainly write down local terms that accomplish what I want. For Lorentz invariance, there's a similar story. So remember that V mu is this particular combination of Goldstones. So if I can write something covariant in V mu that reduces to those particular structures that I expand at quadratic order, then I'm good to go. So up to quadratic order, V0 is this, V vector is this, and one can show that the local structure that I just gave you, regardless of what these powers are, the local structures that I gave you are certain interpreting this expression on the right-hand side, expanded to quadratic order, are certain particular Lorentz invariant derivatives, combinations of derivatives acting on V mu, where D parallel is V mu, D mu, and D mu perpendicular is this other combination. So bottom line is that we can implement Pauli-Villard that we need for longitudinal and transverse separately by adding local Lorentz invariant counter terms to the Lagrangian. And if we do that, we find rho plus p equals 0, even though Lorentz invariance is spontaneously broken. Okay, now perhaps more surprising is the dimensional regularization check. So first of all, is this Lorentz invariant? Well, it is because it's equivalent from the viewpoint of the V mu effective theory before expanding in perturbations. It's equivalent to formulating the V mu effective theory, which is manifestly Lorentz invariant, in d+1 dimensions. Okay, so it does not, at this point, it's like doing dimensional regularization in a relativistic theory. It does not affect Lorentz invariance. Now, if we regulate those integrals that I gave you with the dimensional regularization, we get trivially 0 because they are scaleless integrals. Okay, we have gapless Goldstone modes. There is no mass scale in those integrals. There is no masses in propagators, and there's no external momenta because these are expectation values at 0 external momentum. So they are scaleless integrals, so they are trivially 0. So of course, rho plus p is 0, but in a kind of trivial, anti-climatic way. Okay, so let's instead try to make it more interesting, more difficult. So let's couple the framid to a matter scalar field, for instance, scalar phi, which is massive. And I'm going to couple, at least to quadratic order in all perturbations, I'm going to couple the scalar, and to lowest order in derivatives, I'm going to couple the scalar to my framid in all ways allowed by symmetries. And again, you can check that to quadratic order in perturbations and up to total derivatives, these are the only couplings that I can write down. And then expand to quadratic orders. So I get the same Goldstone action that I had before. I have the action for my relativistic scalar, massive. And now I have 3 couplings that manifestly violate Lorentz. Okay? So not only this part violates Lorentz, but now I have 3 couplings that violate Lorentz. And since they involve phi, and phi is massive, now the dimensional regularized integrals are going to be highly non-trivial. Well, I say highly because I know they're going to be non-trivial. Then you see that, in fact, they're highly non-trivial. Okay? So now I'm going to do the same.
Sorry, I have a question. Maybe that's a confusion. So suppose without CP, constantly without alpha, just a framing. Can I see this Lagrangian for a frame Lagrangian also have some kind of, but it's not Lorentz symmetry, but it's Lorentz environment. We are citing the light velocity to CL. Can I say this way?
Well, but you see, but there's CL and there's CT. No,
if I cite CT to 0, do the Lagrangian have some enhanced symmetry? I mean, there should be some.
No, but you see, but the transverse guy still appears here. So.
Oh, okay, got it. Yeah, okay, sure. Thank you. I got it.
Okay. Now I didn't get it. Sorry. Now I have the same question. Sorry, because if they're just the sum of these 2 terms, one of them has a Lorentz symmetry with one value of C, the other one has a Lorentz symmetry with the other value with a different value of C. That's not enough to explain this Lorentz invariant form, not for this case, but for the previous case when you didn't have the scalar.
Well, but you see, but you want the regulator to be invariant under the true Lorentz symmetry, which is neither of the 2. So it's a tricky question, no? Because
I see.
You're asking a question about.
I got it.
Yeah.
Yeah. No, I see what you're saying.
Okay, and now it's more complicated because we have a massive scalar with some further couplings that violate Lorentz. So in this case, there is no residual or fake Lorentz symmetry at all. Or at least I could not find one, okay? Okay, so now you do the same computation. So you derive the stress tensor in terms of the fields, and it takes this form, okay? So it's some complicated non-Lorentz, manifestly Lorentz covariant expression. There's a minor simplification that you can play some tricks by changing the units and setting one of these couplings, B3. So these couplings are arbitrary couplings now, B1, B2, and B3. They have to do with these couplings here. So B1, B2, and B3 are 3 independent coupling constants. By changing units, you can show that you can set B3 to 0 without affecting P over rho. In particular, if you have P plus rho equals 0, it's not affected by this change of units. But let's forget about that. It's a minor simplification. Bottom line is that after you set B3 to 0 by this clever change of units, rho plus p becomes a d+1 dimensional integral. Remember, we're doing dimensional regularization now. I'm still using point splitting now, of certain derivatives. I have omega square, and I have k here, and then I use the k square. I manipulated things a little bit to write it in the simplest possible form. So it's a certain function of omega and k times the 2-point functions, Whiteman 2-point functions in momentum space now. And now they are a matrix because I have the eta component, the eta fields, and I have the phi field. Okay, so there's a matrix. It's eta eta, it's phi phi, and I also have mixing terms. Okay, and also you have to deal with the fact that the Whiteman 2-point functions, when you give up manifest relativity, they are related to the Feynman 2-point function by some dispersive integrals like this. And in particular, if you have a matrix, it's kind of a mess. If you have a matrix with mixings, it's kind of a mess. Okay, so you have a multiple integral of Whiteman 2-point functions. The Whiteman 2-point functions are themselves dispersive integrals. Okay, so we were able to do all integrals in omega, but we got stuck with the final integral in dk dimensions. So the final k integral in dimensions. And when I say we, I mean us and also Mathematica. Okay. And what we could do was perturbation theory in these couplings, B1 and B2, that mix the framid with the phi field. So we did that, okay? So to lowest order, quadratic order in the couplings, the linear order terms cancel because they come from mixings, the main effects. To lowest order in B1 and B2, rho plus P happens to be a sum of 11 terms of integrals of this form. We have propagators or certain manipulated propagators. You see there is CL here. The denominators have certain powers. I will give you the table of coefficients and powers in a second. So I have powers of k, powers of these denominators, and powers of k squared plus n squared square root, which should be omega k. Okay? And for generic alpha, gamma, and beta, these integrals in dimensional regularization happen to be this mess involving gamma functions and more general hypergeometric functions. And the coefficients CA and the exponents alpha, beta, and gamma are given in this table. Okay, so we have 11 terms with fairly generic coefficients and fairly generic integer, luckily, exponents. So all these 11 terms are a mess. When you sum them together, you get rho plus P equals 0. Okay. I should wrap up. So we checked that this is not an accident of how we do computations. Maybe these zeros are trivial because we are missing something. Maybe we are closing contours in the wrong, I don't know, in the wrong plane, and so we're getting trivial zeros. So I don't know why we could get zeros out of that absolute mess. But we check the same for the superfluid. For the superfluid, we don't expect rho plus P equals 0. In fact, we have examples like, I don't know, liquid helium, in which rho is dominated by a mass density, which is huge, compared to P, which is a very non-relativistic pressure. So certainly we have superfluids for which rho plus P is definitely not 0. And we did the same computation. So a superfluid is described in terms of a scalar with shift invariance about some non-trivial state that depends on the chemical potential. And then we did the same expanding in the phonon field. We coupled the superfluid to a matter field in all ways allowed by symmetry. We performed exactly the same computation, and we get rho plus P different from 0. And in fact, we have an independent, in another paper that I'm publishing with other collaborators soon, we have an independent check of this exact result, meaning we get exactly the same result, not only different from 0, but with exactly the same coefficients and everything, doing the computation in a completely different way, using path integral methods. So the bottom line is this. So this framid, even though it's an hypothetical system, it appears to be a consistent effective theory that describes the broken phase of Lorentz invariance with the 3 Goldstone bosons. At least at one loop, it has an expectation value for the stress tensor that is Lorentz invariant, even though Lorentz invariance is spontaneously broken. And so even though there is no selection rules enforcing this, you could say that this is enforced by symmetries in a very contrived way. It's enforced by symmetries simply because we wrote down the most general effective theory consistent with those symmetries, and we did the computation, and we find this. But certainly is not enforced by symmetries in the standard sense of selection rules of saying, okay, I have a state with certain symmetries, I have an operator which transforms under these symmetries, so some things must be zero. From the FT viewpoint, at least in the dimensional regularization case, from the FT viewpoint, there are really miraculous cancellations at work here. I have no idea how this, what these symbols even mean. When Mathematica gives me 2F1, I trust it, but I have zero intuition about it. And we have 11 terms like this. And when you put all the right coefficients, they all cancel. And the question is this a curiosity, or can it have any implications for the cosmological constant problem or other hierarchy problems like the Higgs mass? To this, I have no answer. I think the way, if one is interested, I see two ways to actually make progress. One is to find other examples, meaning are there other quantum systems in which are other order parameters that exhibit some phenomenon like this. And the other approach should be, okay, let's understand why it cancels in this way, in the sense that is there a structure in the computation that ensures that these cancellations are going to happen, even though in this language they look totally miraculous. Maybe there's a change of basis in which it's obvious that they are going to happen. But I have no concrete ideas about either of these possibilities. So this is all I have to say. Thank you very much.
So I guess somehow I mean, you know, it's good. Yeah, you were very wise, I think, not talking about the cosmological constant problem, probably, right? But I can't help it. I'm going to talk about it. I mean, one of the ways
you talk about
one of the ways that's very different is that, you know, in the CC problem, of course, we do have counter terms that we can write down that mess things up, right? And here,
yes.
But so here, the thing is that I guess the analog is supposed to be that you have a nonlinearly realized symmetry. So
yes.
Somehow, if somebody handed you this Lagrangian, you wouldn't necessarily immediately recognize that it had some nonlinear. You can, you know, a graduate student can figure out
yes.
the linearly realized symmetries of a Lagrangian, but there's no obvious algorithm for finding the nonlinear realization symmetry.
Correct.
Right? Correct.
Yeah. Exactly. So exactly. So that's exactly the point, I think. Meaning,
if I wanted to take your maximal conclusion, okay, I want to go all the way, like you've actually found the key to the real cosmological constant problem just in this analog somehow. Okay, I guess is that what would you agree that that's what I should say?
Well, yeah, exactly. I think that's
and maybe only for the very specific parameters of the standard model, which, however, are the ones in nature. Somehow there's some nonlinear symmetry, you know, and then that if my now even if I calculate loops, I still find the cosmological constant is wrong. But what's wrong is that when I calculated my loops, I didn't know about this nonlinear symmetry, and if I did, I'd have to do something much more complicated, and I wouldn't find counterterms either. Something like that. Is that?
I think so. I think that's the right way to put it. Meaning, this is an example in which a non-linearly realized symmetry in a very contrived way guarantees that something is zero as if there were a standard selection rule, something like that. But the standard selection rule cannot be there because the vacuum spontaneously breaks that symmetry. But in the end result is the same. So, for instance, for the cosmological constant case, now we always say supersymmetry was a candidate symmetry to enforce that the that the cosmological constant is 0. And however, supersymmetry is clearly broken. Okay, so now this shows that you could have a symmetry that is spontaneously broken and still have certain expectation values that violate that symmetry vanish, as if the symmetry were unbroken. So I think it's exactly what you're saying now. The question is there a secret, non-linearly realized symmetry that enforces that the cosmological constant is 0, but not in the standard way of non-linear realizations. No, meaning, yeah, I'm a little confused by what the statement should be, because also non-linear realizations. No, we know that, okay, non-linearly realized symmetries enforce that certain things are 0 in the Lagrangian. Meaning it does not, that's what the symmetry statement is. Certain things are 0. But this is more like it's an interplay. It's an interplay between terms in the Lagrangian and I guess selection rules for expectation values. I don't know. I'm a little confused by the general lesson here. Meaning how to extrapolate it. Because, for instance, let me give you why. Let me tell you why I'm confused. Because it's true that in the Lagrangian here, we could not write down a term, a counter term that would violate this. Okay. However, we all also know from general properties of renormalization theory, let's say, that we need the Lagrangian must be able to accommodate all counter terms that we need to cancel UV divergences, okay? But it doesn't necessarily have to accommodate finite pieces from loop integrals. Now, in particular, for instance, in standard particle physics, we get non-local structures from loop integrals, and those are certainly not associated with local counterterms. No. So one possible loophole here could have been, before doing the one loop computation, could have been, I look at 3 level, T mu nu is 0, T mu nu is Lorentz-invariant. But could it be that from loop diagrams you get that the UV divergences are Lorentz-invariant because the counter term that you have a Lagrangian only can give you a Lorentz-invariant expectation value T mu nu. But could it be that you get some finite pieces out of the expectation value that are not Lorentz-invariant? This would be consistent, I think, with renormalization theory. And it would break somehow the connection between what I can write down in Lagrangian and what I can find in an expectation value. You see what I mean?
So when are you doing the 2-loop calculation?
You win.
I don't know if how my student wants to do it. I don't want to do it. Or if some of you want to do it.
So in a one loop, this you got this vanishing this cosmic constant. Is the eta is the Gaussian boson? That is the essential part. For example, if I adding a mass to the eta, do you expect you get some non-vanishing cosmic constant?
Sorry, I did not understand the question. Can you repeat? Maybe close to the microphone.
Eta is the exact Gaussian boson in calculation.
Eta is an exact Gaussian boson.
I'm trying to say, if you add something like the mass term or something, break it, it's a Gaussian boson mode. I think you will get some contributions to the cosmological constant, right?
Well, in that case, you'd be breaking Lorentz explicitly, because the vanishing of the mass for the Gaussian boson is a consequence of Lorentz invariance. No? So in that case, you'll be breaking Lorentz explicit, so I don't know what to expect. Probably, yeah, I would expect terms that violate Lorentz also for the minimum.
I kind of want to come back to my question, so to kind of push you a little bit more on that, okay? Because I'm just trying to imagine, you know, if any story like this, you know, could be true for the standard model, right? But like one criticism I could have you know, or just the question I have is that, you know, I said, you know, graduate students can't find nonlinear symmetries, but I don't know, maybe professors can. In other words, there's a vacuum manifold in this theory that's parameterized by eta, okay? So maybe in the standard model analog, we don't know what eta is. In other words, it's some field that couples very weakly, or that could be one story. But it could not be I don't know, it couldn't be the Higgs boson, presumably, or, you know, maybe, I don't know. So anyway, I'm just trying to push you a little bit, and I'm just saying that everything here, the mystery and the solution looks to me like it has to do with this mysterious goldstone. And so it's hard to imagine how to, if I wanted to be maximalist again, how to even tell a story at the word level for the standard model.
I don't know.
That's a totally unfair question because you're not claiming anything like that. I have to ask, right? Come on.
Well, it's a good question, but frankly, I have no idea. I think so. I think this is one. My take on this is this. This is an example of something quite unusual. So the question is it an isolated example, or can we find more? And if we can find more, maybe we can start building an intuition about when to expect something like this. With one example, I don't know. I frankly don't know. No, you see what I mean? Meaning, I don't know what the general rules of the game are. I don't know.
For the cosmological constant, you use dimensional regularization. Also, don't see the power divergence. You can get the mass to the fourth contribution. So if all your fields are massless, you also don't see that. Now here, I don't know how you can compare with this problem.
You could integrate out a massive field. I mean, but that's essentially, I think that's essentially what poly-VRs is. Right? I mean, that's the way you would see the cosmological constant in dim reg. You would just integrate out a massive field.
Yeah, I mean, but suppose all your fields are massive. But there's no massive field, only massive field. You also don't see any divergence, well, whatever contribution to the cosmological constant. Using dimensional regularization. Now here you only have goldstones, so they are all massless. Anyway,
well, but here, that's why here we introduce the massive matter field and coupled to it, because yeah, in dimensional regulation, some things are too trivial to be interesting, I think. So unless you spice them up a little bit. Meaning there are some zeros in dimensional regularization that it's hard to, at least for me, it's hard to relate to. Yeah.
I mean, in the spirit of trying to understand it somehow more physically, like when I look at this, the thing I have no idea it seems like it's a very technical point and sort of. I mean, I agree with everything you say, but it's all very technical, and it has to do with this. You say, oh, well, you know, you need a regulator that preserves this, and then I don't have to worry about the measure. If I had the wrong regulator, I would have to worry about the measure. And I'm wondering if there's something there that could be understood a little bit more physically, right? So it's specifically, and I'm thinking in terms of Schrodinger picture, okay? Now somehow because you said, and I'm curious about this, is in, you know, if you do you should of course see the same subtlety in canonical quantization, right? But in canonical quantization, in Schrodinger picture, you just have some wave functions and you just have the operators acting on them. But I think if you have a goldstone, you know, you basically, it's kind of like the difference between saying that the wave function is a function of pi, the goldstone field, or the wave function is a function of e to the I pi. So there's something kind of global going on there, right? That has to do with the fact that, you know, you have this this shift symmetry is somehow built in already to the. I'm just babbling, okay, but I just wondering, like, if you, instead of saying, okay, that's a technical problem, and I'm just going to use dimreg or polyVRs where I don't have to think about it. I'm wondering if thinking about it can help you understand, because there's something subtle here. And right now it seems like it's buried in this regulator. And is there something there you can?
Well, first of all, physically, I think this argument that I gave you at the beginning about how to now take the expectation values of mu and perform a little boost, you get something that usually you don't get. Meaning, if you are assuming that the goldstones diagonalize momentum, you shouldn't be getting this. And magically, the framid, so different systems avoid this subtlety in different ways. The framid avoids this by setting rho plus p to 0. So in a sense, this argument is already telling you that probably this is going to be true to all loops, because otherwise you cannot have goldstone excitations that are eigenstates of momentum. And if they're not eigenstates of momentum, then translations also have to be broken. So I think this is already a good physical argument, but just to be sure and to see how it works out at one loop, we did the computation and we discovered these cancellations. Now, for what you're saying, well, we know that the wave functional for spontaneously broken symmetries is a function of the goldstone and not just of e to the I pi, meaning that that's exactly a statement of spontaneous symmetry breaking, not that the state is not invariant. So the wave functional must depend on the goldstone in a non-invariant way.
Well,
No?
by the way, I think we should stop and let people, leave who want to leave. But if let's clap again for Alberto. Very interesting seminar. Yeah. So.